Okay, so in this one, we are continuing still with the principle of work and energy. Notice that in this problem, we have a block again, we have a spring, we have another force that's acting diagonally. So let's see what the problem says. The spring is placed between the wall and the 10-kilogram block. If the block is subjected to a force F of 100 newtons, determine its velocity when S equals to half a meter. When S equals to 0, the block is at rest and the spring is uncompressed. The contact surface is smooth. So once again, they're asking us what will be the velocity once you compress the spring half a meter. So let's write down the givens. So we're already getting here the mass is 10 kilograms. We have a force given here as 500 newtons. We have the initial velocity, or I can write as V1 is equals to 0 meters per second. We have the stiffness of the spring as 500 newtons per meter. And the compression here, it's 0.5 meters. Or we can say S2, because we start from 0, I can do delta S. So it is compressed half a meter. All right, and we are looking for what is the velocity when it's compressed that amount. Okay, so once again, the equation should be T1 plus the sum of 1 to 2 of the works is equals to T2. So let's draw our free body diagram of the system to analyze it. So in this system, let's see how many forces can we find. So first and foremost, you guys already know that we have gravity. So that will be mass times gravity or weight. We will have the spring force. So notice, if we're going to be pushing to that side, that means that the spring is going to try to push on it, right? So the force on the spring will be that one. Because this is resting on the surface, I should also have a normal force, right? A normal force right here. And we have the force over here, the 500 coming at a diagonal. Notice we do not have an angle, but we have that 354 special triangle, so we can use that to figure out our stuff. All right, so if we substitute here in the equation, this will be 1/2 mass times B1 squared plus the sum of works. So right away we know that there's two forces that are not going to be doing work because we're only translating in the x direction. Normal is perpendicular, weight are perpendicular, so these forces are not causing work. So normal force and the weight do not cause work, right? Because they are perpendicular to the direction of displacement. So that leaves only the 500 and the force of the spring to do all the work. So with the spring, all right, so this will be plus the force of the spring. So I'm gonna say here's force of the spring times S, or not, no, this is force F, the 500 times delta S. And this will be minus 1/2 the force of the spring, which is K, times delta S square, equals to 1/2 mass times V2 square. So because we start from rest, this one goes to 0, right? So we can just rearrange that. So then the force, this will be 500. And we can do the cosine of the angle, right? So there's an angle right here. So we can do that. So whatever angle theta, this is 534. So cosine of theta, it's equals to adjacent over hypotenuse. So instead of using cosine of theta, I can just do then times 4/5. That will be the component of force acting in that horizontal direction. And that will be times the half a meter. that I am moving. And this will be minus 1/2 times the 500 newtons per meter for the stiffness times the 0.5 meters square that we are displacing. Not because we start from 0, I can just do that one square. And this is equals to 1/2 the mass, which is 10 kilograms, times V2 square. So it's a plug and chug, solve this value, find this value, rearrange, and we should be able to figure out V2. Out of this, I think I should get 200 minus 62.5 is equals to 5V2 squared. So when you rearrange this, you should find out that V2 is equals to 5.24 meters per second. So once again, we don't have to use the kinematic equations to solve for this problem, because using the principle of linear, or the principle of work and energy, we can find this approach. So that is it on this video. I'll see you guys on the next one.